Yep.
When you're doing the cross multiplication, you're just looking at the numerator, correct? Just ignoring the denominator. You're just bringing n to
I'm multiplying like this and like
n to
this.
the fourth or 4 minus 1. And then you just ignore the n times n minus 1.
N times n minus
Multiply 2 though, right?
n times, wait, what? And ignoring the
Yeah,
n.
because it wouldn't be n over n, right? You're just looking at the numerator for both sides when you cross multiply.
Yes. Look, I hate cross multiplying. I hate it because it's algebraically, it's bullshit, all right? What you're doing is clearing fractions, okay? That's all you're doing. But everyone knows cross multiply, and so what you're technically doing at this point is you're saying, I don't like this fraction, I multiply n here, okay? N's go away, right? And then you're saying, I don't want n to the fourth minus 1, so I do n to the fourth minus 1 here, and n to the fourth minus 1 here. And what happens over here is the n to the fourth minus 1's cancel. So it looks like all I did was multiply this times this, right? And it looks like all I did was took that and multiplied here. That's what it looks like I did. And it's taught in the, I told you about the math purgatory. There's a lower place for the people who teach cross multiplication. Okay, there's a lower level, right? I'm not going to be down in there at least. Yeah, I know. You can't blame the teacher. It's cute, it's fast, it's easy, but then when you get to classes later and you're like needing to know why that works, like what's going on, you're like, just cross multiply. Well, what are you doing? You're just clearing fractions, right? That's all you're doing. So does that help?
Yeah.
Okay. Yeah, I should be punished for even saying it, but okay. Good? Okay, now pay attention. I'm going to change this problem just a little bit, and I want you to see the chaos it causes, all right? So what I'm going to do is I'm going to take this problem again. I'm asking you to pay attention because I like to give problems like this. Because this is, I mean, once you know what to do, this is pretty straightforward, right? I mean, this is pretty straightforward. So I want to take this problem, and all I want to do is change that to a +1. That's it. Seems so like subtle and so like nothing's going to matter, everything's going to be great. Okay, now, does it change the fact that we want to compare that to a harmonic? No, it doesn't, right? We should still compare this to a harmonic because at the end of the day, the +1 makes very little difference when n is big, and so that still does look like n cubed over n to the fourth, doesn't it? So 1 over n seems like a great candidate for this. This is divergent because it's harmonic. All right, so what do I need to show? What do I need to show?
That a sub n is greater than or equal to
Yes.
1 over n?
Yeah, so the a sub n's have to be bigger than that, right? Because if these add up to be infinite, then I need those to be bigger than those so that I can say that these add up to be infinite as well. Okay, so now I need to show n cubed over n to the plus 1 is greater than or equal to 1 over n. And we do that same thing, right? We clear the fractions, right? We clear the fractions. Cross multiply. Okay, so when I clear the fractions, what's the inequality say? N to the fourth bigger than or equal to what? N to the fourth plus 1. Plus 1, right? Not minus 1 this time. And then I subtract n to the fourth on both sides, and I get what? 0 is less than or equal to, or 0 is greater than or equal to 1. And that is not true, right? That is not true. You see what a slight difference that made? I cannot draw a conclusion now. I can't. I cannot say, oh, this converges. I can't say that, right? We just talked about that. If you do a divergent comparison and you get your inequality to not work, it just means that the test didn't work and that your choice wasn't good enough to draw a conclusion. But it seems like this should be harmonic. I mean, we only changed one little thing, right? Just one tiny little thing, okay? So what I'm going to do is I'm going to go back here and I'm going to look at what went wrong. What went wrong? When I cleared the fractions, right, and I got the n to the fourth there, on the other side, it was the plus 1 right there, right? And it was this plus 1 makes this side bigger than this, yes? If you switch this, what happens though? You can't, I don't know if that's what you mean, but you can't switch this, right?
Move the x to the fourth to the other side, no 1 to that side. That wouldn't affect it.
If we, no, because if you, well, no, if we move that to that side, right, we'd have -1 greater than or equal to, and then we take away, we get that, and that's not true, right? So the problem, so this is the part you have to pay attention to, right? Because what I'm going to do is I'm going to be clever, all right? I'm not a clever person, but I'm going to be clever this time, right? So the problem here was that the end of the fourths went away, right? And it made this a 0. Made that a 0. I actually have control of one of those. Which of these two, the one on the left or the right, do I have control over? The one on the left. Why? Where did it come from? Yeah, cross multiplying. Yeah. Right? It came from this to here, right? This to here. And I chose this 1 over n, right? I have control over this. Wouldn't it have been a lot nicer had this been even just 2n to the 4th? What if this was 2n to the 4th? Just look at it. I don't have a red. Yeah, who cares? I have blue. What if this had been a 2n to the 4th? What would have happened? Subtract n to the 4th on both sides, what do you get? N to the 4th greater than or equal to 1. And would that have been true? Yes, that would have been true, wouldn't it? That would have been true. Yeah, exactly. So wouldn't it have been nice to have a 2 here? So could I just put a 2 right here? I could put a 2 here, couldn't I? And then when I do that thing, it would be here, yes? I have control over this. Could I change it to 2 here then? Does it change the divergence? No, it's still harmonic. It's just, I just put a constant. So this is still a constant over a linear expression in n. Do you see? What I'm doing is I'm tweaking some of the algebra. Well, I'm tweaking a number to make this thing work, but I'm reverse engineering it, right? It's like I'm saying, crap, this sucks. I wish I would have had maybe a 2n to the 4th here. Can I make that happen? Yeah, if I put a 2 here. Does putting a 2 here change this? Because you have to be careful. What can you not put here? Like someone might have said, let's make this n to the 5th. Because n to the 5th would eventually be bigger than this. But if you change this to an n squared down here instead, what happens? If that's n squared, does it still diverge? No, then it's a p series, p is 2, it'll converge, and then your inequality is the other way around. So it's like you're trying to tweak without overstepping. So let's just recap. I did this, it didn't work. I analyzed what went wrong, and I did a revision of my comparison to 1 over 2n. That's still a divergent harmonic series. Now my inequality still has to be this. I put the 2 there, I do that. That gets me to here. This is no longer part of our work. And then from here to here is true. And therefore, I can conclude that the original series, what? Diverges. Okay. Yes?
So, when you're taking the compared series, can you only add a constant? For instance, let's say it's just like the same 1 over n. Can you only multiply it by the constant, or are there times when I'll have to like add a constant?
You can do whatever you want. You can do whatever you want to this. You have complete control of this. The thing that you need to be careful with is that whatever you do to tweak this, you better still know what it does, right? Like you can't tweak it to the point where you don't know what that does. Like you're trying to figure out what this is and then you compare it to something you don't know what it does. You have to compare it to something you know. So tweak away, do what you want. Now, if you tweak too much, it might change this though, right? It could change from, like that's what I was saying. If you changed it to n squared, right, it's no longer divergent, right? It's convergent because that's a p series, p is 2. And now since this is convergent, you would only be able to try and show that that converges, so you would have to show this inequality, and I can tell you right now that won't work. So I don't know if I'm answering your question. Do whatever you want over here. Anything you want. Put a shit. You could put an e to the n here if you want. It doesn't matter as long as you know what it does. Okay? Yes. Was that a question?
Yeah, I'm trying to understand what I'm asking. But okay, so if you're whatever you're comparing it to, whatever you choose it to,
Yep.
whatever you know if it converges, then that's when you're gonna want to like show that the new one you're comparing to is bigger. But if it diverges, then you want to show the initial one's bigger. Is that
Yeah, you could say it that way. You could say that way. If the one you're comparing to converges, you want to show that these are bigger than those, right? If this one diverges, you want to show that those are bigger than these. Is that what you said?
Yeah.
Yeah.
Yeah, I'm trying to.
Yeah.
It says it right here too.
Yeah, it's on your test. I mean, it says it there.
Yeah.
Yeah. Okay? Ready for another one? Good. All right.
And even if you did like 2 over 2n for that problem, you would still run into the same problem, correct? Of like,
If you do 2 over 2n, yeah.
yeah.
Okay, what the hell is going on? Hold on, my computer's acting weird. Where's my, oh, there's my mouse. What I have? Invalid, what? All right, so we just did that one right there. All right. So I hope I've given you just a couple examples, 3 examples of the convergence test, right? Sorry, the convergence test. What the hell am I talking about? The comparison test, right? Within the comparison test on your chart there, there's something. There's like I think there's an A, B, C, or 1, 2, 3. Let me see. 1, 2, 3. See them? 1, 2, 3.
You say comparison?
Is it on comparison? Let me see again. Yeah, right here. That's what I'm talking about. 1, 2, 3.
Oh, yeah.
See?
Oh,
Okay.
nice.
The eyes. The eyes. Okay. Yeah, the 3 eyes. Okay, so within the comparison test, there's another sort of adaptation of the test. And students love this because it doesn't require that you like mentally figure out this like which one needs to be bigger than the other one, right? There's no confusion with that. And it is called the limit comparison test, but it is just the 3 eyes in that box. And here's what it says. The limit comparison test says, all right, look, you still have to figure out a series to compare it to, right? You still have to do that. You start with a series, you're going to figure out something to compare it to, but instead of trying to show the inequality is true, all you have to do is take the limit of the ratio of the sequences. Let me see, right there. I'm going to put it right there. So we're going to take this a sub n right here. This is our original sequence that's given to us. We're going to compare it to something over here that we've got to come up with, right? We've got to come up with that. That's up to us. Now, we do need to know what this does. This is either going to converge or it's going to diverge. It depends on what we choose, right? Like we choose 1 over n, it's going to be harmonic, it diverges. We choose 1 over n squared, it's going to be P series, it's going to converge, right? So we're still going to do a comparison. We still have to figure this shit out on our own, but forget the inequality that might be confusing you. What you're going to do instead is this. You're going to take the limit as n goes to infinity of that sequence over that sequence. And what you're going to hope for is that this turns out to be a constant, C. Now, when I say constant, it's not just any constant. This constant must be, what does it say? Does it say?
Positive real number?
A positive real number, right? Positive real something. What does it say exactly?
C for some positive real number.
Positive real number. This C that you get must be positive, and it must be a number, which means it can't be 0 and it can't be infinity, right? It's got to be a number, not positive number, not 0, and it can't be infinite. Like if you get infinity, it doesn't work, all right? Okay, well, let's see. Then let's do this problem again. What do y'all say? We do this one again? The one that caused us a little bit of trouble? Because of that +1 down there, and I had to tweak it, which people didn't seem to like. Right? I mean, I understand. It's not a natural thing to tweak that like that. It's not. So let's compare it to this series, which is a divergent harmonic series, right? I'm still using 1 over n because this, again, does look like n cubed over n to the 4th, so it does look like 1 over n to me. But now, I'm not going to set up the inequality. I'm going to set up this comparison, this limit. So I'm going to do the limit comparison. I'm going to take the limit as n goes to infinity of that sequence, n cubed over n to the 4th plus 1, over this one, 1 over n. That sequence, the sequence of that series, divided by the sequence in this series. And then you have a fraction over a fraction, right? So you can flip it up. And when I flip that up, it becomes limit n goes to infinity of. When I flip this up, n to the 4th over n to the 4th plus 1. Now, when you take that limit, you get infinity over infinity, right? L'Hopital. L'Hopital. So from here, because I'm getting infinity over infinity, L'Hopital, limit n goes to infinity. What's the derivative of the top? 4n cubed over the bottom? 4n cubed again, right? 4n cubed. And algebraically, that just turns into 1, right? That just turns into 1. And is 1 a positive constant? Yes, it is. So what is the conclusion? The limit comparison test says, if this limit, right, if this limit comes out to be a positive real number, then what? What is the conclusion? Then both series converge or both series diverge. In other words, whatever one of them does, they both do. And don't we know what one of them does? We know one diverges. That means they both diverge. Okay? That's a little nicer, isn't it? Yeah, right? Questions? I need to draw my conclusion. But this is a positive constant. Constant. And so, therefore, I'm not going to write it. I'd put 3 dots. Therefore, this converges. But on your work, you need to draw your conclusion, right? You have to actually go back and say what you can say at the end. This diverges. All right, let's do the first problem we did. N equals 1 to infinity. Oh, no, you know what? Let's do your quiz. Let's do your quiz. Wasn't that your quiz? And you did the integral test, didn't you? Because I told you to do the integral test. I wonder if we could do this with a comparison, or even better, a limit comparison. So when n gets really big, really, really big, what's dominating that expression there? E to the n. I'm going for it. Look, I don't even know if this is going to work, okay? I'm going to go with this. I'm going to try and compare it to this. Now, what kind of series is that? Careful. P series. With P series, your n is in the base, not in the exponent. This is geometric. That's 1 over e to the n is the same as 1 over e to the n, right? And what's 1 over e? Well, some number that's bigger than 1 or smaller than 1? This number is smaller than 1, isn't it? So this is a geometric series with r being equal to 1 over e, which is definitely less than 1, which means this is what? Convergent. This is convergent. Okay? So I'm about to take this series. By the way, on your quiz, what was your answer? Was it convergent or divergent? It was convergent, right? Okay, so I'm about to compare this to a convergent series. Do y'all see how I picked this series and why it's geometric and why it converges? Everyone good? Okay, now I can do the inequalities or I can do the limit. Y'all want to do the limit? Okay, so I'll do the limit. Do limit comparison. Limit comparison. I'm going to take the limit as n goes to infinity of n over e to the n over 1 over e to the n. Shit. No bueno. What happens here? What does that become? Limit n goes to infinity. What happens when I flip that up? The e to the n comes up here, right, over 1, like that. And then e to the n's cancel, and you just get what? N. And what's that limit? Infinity. Is infinity a positive constant? No. So what happened? It didn't work. This didn't work. Damn. Now that doesn't mean you say that's divergent. That just means that this didn't work. Okay, all right, that's okay. I'm not going to panic. I'm going to try it without the limit. I'm going to go to the inequality. So this bucket of numbers, right? This bucket of numbers adds up to be a number. So if I can show that these are what? Smaller than those, right? I want to show that those are smaller than or equal to those. Right? And then do our thing. Do our thing, do our thing, do our thing. E to the n times n less than or equal to e to the n. Divide both sides by e to the n. Guess we could have done that. See, if you clear your fraction, no, I'm just going to shut up. Divide by e to the n, and you get this. Is n less than or equal to 1?
Yes.
It's equal to 1 once, and then after that, it's not, right? Is that going to keep holding the whole time? No. Shit. That failed. Okay. What's the moral of the story here? Yeah, this is the nature of series, is that you've got to figure out the test that's going to work, right? We know the integral test works because you did your homework, right? Or your quiz. We know the integral test works. As great as the limit comparison test is, it's not the magic pill, right? That's why we have a table of tests. If there was one test for everything, that's what we would, here it is. Here's the test for series, right? But there's not. So we have to have different tools for different situations. The problem that we had done earlier, like the first time I showed you the limit, right? Man, it was like beautiful. It worked out perfect. It's like, yes, I wish I would have thought of that first, right? So again, that's going to be part of your challenge, is that when you get a problem, is like applying the right test. There's nothing that really indicates what to do first. Yeah. Okay, so we know the integral test works, right? But the comparison test absolutely does not work, no matter how we try it. Well, comparing to this, we could compare it to something else, but I can tell you right now, there's nothing you're going to be able to compare it to. Like, it's not going to happen. Okay, so, but at least we know the integral test works, right? All right, let's look at one more example. Natural log n over n squared. This is a similar problem to the one we just did. All right, so if we start this problem from the very beginning, we would first say the nth term test to see if we get lucky, right? Take the limit of that as n goes to infinity. You get infinity over infinity. Use L'Hopital's rule, you get 0, which tells you nothing, right? So we move on. Is it geometric? No, I don't see an n and an exponent, right? So it's not geometric. Is it harmonic? No, it's not a constant over linear, right? Not harmonic. Do I want to do an integral test on that? Yeah, no thank you. I don't think so. I don't think I want to. I could probably integrate it, right? Natural log x over x squared, I could probably do some integration by parts, maybe get it to work. But I really am leaning away from integral tests unless I absolutely need it. Comparison. Okay, well, are these, as long as what I plug in here, I'm always going to get positive numbers, right? Well, natural log should give me positive numbers as long as n is bigger than 1. So initially, what's natural log of 1? 0. So initially I'll get a 0, but after that everything's positive. So it should be okay. So I can do a comparison. Compare to what? Try 1 over n squared? Yeah, that seems reasonable. If this doesn't work, you might try 1 over n. I don't know. I mean, I need to know what that does. Do you know what that does? Converges. Why? What kind of series is this? P series. This is a P series. P is 2. That's bigger than 1, right? That means we have convergence. How do you know P series converges if P is bigger than 1? Well, because that's what I told you at the beginning of class, right? And then I said we could prove it with the integral test, but we're not. We're just going to take it on faith. And now from here on out, when P is bigger than or equal to 1, no, sorry, when P is bigger than 1, we get convergence. When P is less than or equal to 1, we get divergence. So we have a convergence series we're comparing it to. Now, would y'all like to do the limit, or would y'all like to do the inequality? You want to do the inequality? All right. So this bucket of numbers adds up to be a number. So we need these numbers to be smaller so that they add up to be a number as well. So I want to show that the natural log of n over n squared must be smaller than or equal to 1 over n squared if you clear out your n squareds. All I did here is multiply both sides by n squared. Multiply both sides by n squared. Is that true? Is the natural log of n always smaller than 1? Only in the beginning, right? When n is 1, this is true. But after that, it's not true anymore. Right? Natural log function grows. And so it's not going to stay less than 1. So this failed. Okay, so I don't know. Try the limit comparison. Take the limit as n goes to infinity of the sequence over there, the original sequence, over the one we're comparing it to. See, because sometimes this works and this doesn't. Like sometimes the inequality doesn't work, but the limit does. So you do want to try them both. Y'all understand what I'm doing here? I'm doing that 3i whatever on the page. Okay, what is this? This is the same as limit n goes to infinity. When I flip, things cancel. What are you left with? Natural log n. Shit, that goes to infinity. Right? That goes to infinity. This failed. Do what? You could try something else now, okay? But I can tell you right now, it's not happening. You can try a bunch of different things. It's not happening, all right? So I hate doing this to you. I hate like saying, hey, look, everyone, we got this great test called the comparison test. See, look, here's how it works. And then I show you like 2 examples where it fails. But that's just, again, because we're going to move in, we need more tests, right? We need more arsenal, more in our arsenal. So that pretty much finishes out that section, okay? I put here at the very end, this is the example I did right here. I said, so what do we do here? You know, what do we do? Well, we move on. We move on to the next section is what we do. We realize that as good as things, well, As good as things are, they're still bad. How are y'all feeling? It's a bit intimidating as a student to realize that you're going to be presented with the series and there's going to be no prompting. Now, when you're doing your homework, at least you know what section you're in, right? So when you're doing your homework, you're like, okay, this section covers integral test and comparison test. So it's going to be one of those, most likely, right? But when you're in some other class, like you're studying computer science and you're trying to figure out what a series does, there's not going to be anything that says, oh, you know, this is harmonic. You know, there's not going to be, oh, use a comparison. Like, there's no prompting, right? So, yeah, it takes a while to get comfortable with this. All right, other tests. Here we go. So we are now in the next section, 8.4, other convergence tests. And the first one that we're going to look at is called the alternating series test. Now, the alternating series test is not going to help us at all with the problems that we just got stuck on. The two problems that we just tried that we couldn't get with the comparison test, this test isn't going to fix the problem. But it's the first one out of this section, so let's talk about it. So we all remember what an alternating series is, right? An alternating series, and pay attention to the notation here because I need to point something out that's important with alternating series. And that is, when you have an alternating series, right? If somebody gives you a series, right? And it's alternating, then you can rewrite it where you have -1 to the n, or you could do -1 to the n minus 1. That's going to make it alternate, right? In this case, -1 to the n, you'll start negative, then positive, negative, positive, negative, positive. If you do -1 to the n minus 1, it's going to be positive, negative, positive, negative, right? It's going to be one of those two scenarios for an alternating series. The -1 to the n or n minus 1, that takes care of the alternating. What's left, I'm going to call b sub n. The b sub n is the actual formula for the sequence, the part that's always positive, the part that's not alternating. So it's just like the thing that's creating the numbers, right? And we're ignoring the alternating part, okay? So here I say here the b sub n is the part of the sequence which is always positive. So let's look at some examples here of actual alternating series. Look at the first one, -1/2 plus 1/3, -1/4 plus 1/5, -1/6 plus 1/7. So this is alternating, right? Minus, plus, minus, plus, minus, plus. That's -1 to the n. That creates the alternating. And then 1 over n, if you look at the numbers, this is just, oh, wait. I'm missing something. What am I missing here? It should be 1 over n plus 1. That's a typo. Right, because it starts at 1/2.